Okay, folks, let's talk collisions. Collisions, a little bit about collisions before we get into solving our momentum problems, because we are going to be doing some problems when things are colliding or bouncing off each other or sticking together. So there are different kinds of collisions, and we should get the terminology down. All right, collisions. Now, I got an arrow right, arrow left. Arrow left, we're going to put elastic. Elastic. Elastic, you know what elastic, well, you know what an elastic is, like a rubber band, but that's not what I'm talking about. The elastic means to go boink and bounce off. All right, but bounce off with no loss. You ready for this? You ready for this? You ready for this? No loss of momentum or kinetic energy. All right, so elastic. So elastic collisions. Sometimes they're called perfectly elastic. Elastic and perfectly elastic are kind of redundant. Not just kind of redundant, they are redundant. Okay, they mean the same thing. So elastic, or sometimes you'll hear perfectly elastic. Same thing. This means no loss of KE or momentum. Now, there shouldn't be a loss of momentum in any of our collisions. Conservation of momentum. Momentum before things collide is going to be the same as the momentum after things collide. All right, so that should be the same no matter what kind of collision we have. And what it comes down to, the difference is what happens with kinetic energy. Now, kinetic energy is, in an elastic collision, there is no loss of kinetic energy. Now, kinetic energy is you got a thing moving here and you got a thing moving here. These two things bounce off each other, boink, and they have the same total amount of kinetic energy they had before they collide. That is not a real situation as far as the macroscopic world that we see on an everyday basis is concerned. These elastic collisions don't exist because when things collide, you can hear them collide. Smacky. Smacky is sound. Some of the energy went into smacky sound. So you lose some due to sound. I mean, not a lot due to sound. And if you're in space, you wouldn't lose any due to sound. There'd be no sound. But most of the energy is going to be lost due to, boom, work transfer, deformation. If you have two automobiles colliding and they go, and they're a mess now. Well, how did they become a mess? Some of the kinetic energy went into work to deform the automobiles, to crumple their fenders and blah, 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 blah. That is energy lost that came from the kinetic energy that caused the deformation of the vehicles. Another way is heat energy, friction. Things are going to hit and rub, and there's going to be deformation. Going to cause particles on a molecular level to rub and move. There's heat loss. There is work done due to the deformation change. All of that is coming from the original kinetic energy. So if you start with a certain amount of kinetic energy, car A, car B, okay, all that is loss of energy. So in any collision, there is going to be a loss of energy. Now, some collisions are so nearly elastic, meaning that they lose so very little kinetic energy that we can essentially say, okay, all right, fine, we'll call those elastic collisions and call it a day. Okay? Now, technically, they're not. Unless you're on a molecular scale, an atomic scale with things colliding, that ain't happening. But we can get some collisions that are so close to this, we'll essentially call them, all right, they're elastic. And that would be things like billiard balls bouncing into each other. You know, they're not deforming. There is transfer of energy before and after is essentially the same amount of kinetic energy before the collision, after the collision. It's two super balls, you know, little bouncy balls, they collide, bounce off each other. That would be, or bumper cars, you know, bumper cars, boing! Those would be essentially close enough to elastic that we could call those elastic. So elastic collisions, no loss of kinetic energy or momentum, but this is true of all collisions are no momentum loss, conservation of momentum. But there's a loss of kinetic energy, and that kinetic energy gets changed into heat, friction, and some sound. All right, so this, not really too much of what we're going to be dealing with. And most real-life collisions are of the other kind. Well, what's the opposite of elastic? Super elastic bubble plastic. Inelastic. 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 I think it's a French word. Inelastic means loss of kinetic energy, not momentum. So in an inelastic, you have loss of Ke. And this is what 99.782% of the time I've done the statistics, people. Out of 100, we're going to get some kind of inelastic collision where we're going to lose some kinetic energy. We're not going to lose momentum. No loss of mom. Mom before the collision and mom after the collision will stay the same. Conservation momentum. All right. There is a kind of an inelastic collision. So when things bounce off each other, that is an inelastic collision. Even though they're bouncing off each other, it's still inelastic because we're losing kinetic energy. But there is a kind of an inelastic collision. Put this over. Am I still in the picture? Yeah, okay. Called a perfectly or complete inelastic collision. A perfectly inelastic collision. And in a perfectly inelastic collision, what you have is maximum kinetic energy loss. In a perfectly inelastic collision, you have maximum loss of kinetic energy. All right, if I have two things colliding and they bounce off each other and like they're billiard balls, usually we'll say, okay, call that elastic. If I have two automobiles that come in and one comes in and like glances off the back of another one and they both go skidding on their way, that is going to be considered an inelastic collision. There's going to be loss of kinetic energy. I'm sure it's an automobile, some deformation going on there. But there will be no loss of momentum. In a perfectly inelastic collision, you're going to have things sticking together. You get stickage. That's a word. Trust me, look it up. Stickage. Heard it here first. You get stickage in a perfectly elastic. So what I'm going to do is take we have three different kinds of collision, three different kinds. Sometimes you'll see some people will say, well, there's four different kinds of collisions. You have elastic and perfectly elastic. Same thing, okay? It's one. Inelastic, two, and a kind of an inelastic collision called a perfectly inelastic collision. And in a perfectly inelastic collision, one, things stick together. And you get maximum loss of kinetic energy. You can get actually total loss, but that is very, 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 very rare to totally lose all your kinetic energy after the collision. It can happen. So they'd be like, for example, if you have a car moving down the road, car moving down the road, identical cars, they're identical. They're identical cars. I'm using my Jedi mind powers on you. Only works on the weak-minded. Is it working? All right. Two identical cars moving at each other. No, head on, no angles, no glancing blows here. They're going to head on, hit each other, exact same vehicles, moving the exact same speed. In that case, and they stick together, boom. That would be a stickage, inelastic collision, and we would lose all of the kinetic energy. The kinetic energy it would be totally gone. The momentum before the system was going to be a total of zero. That's interesting. The momentum before they collide would be zero because one's positive. Moving to the right, we usually designate as positive. Moving to the left is negative. If they're the same mass and same velocity, they would have identical kinetic energies in opposite directions, meaning the total energy, total momentum of the system would be zero. And then after they collide, they would stop moving and they would have zero momentum as well. So the momentum is conserved. It was zero beforehand, but they're moving. Yes, they're moving equal and opposite with an equal and opposite amount of momentum, that total zero. And afterwards, they stop moving to zero. The kinetic energy would be, all right, they've got some, you've got some kinetic energy. Kinetic energy is not a vector, so we would just total up the kinetic energy before they collide. Maybe you have 1,000 joules and you have 1,000 joules, that's 2,000 joules. After they collide, they stick, they stop, boom. No kinetic energy anymore. We've lost all the kinetic energy. That would be a perfectly, I would call it actually like a perfectly perfect inelastic collision. Okay, now, you can get inelastic, what I call perfectly inelastic collisions. You don't lose all your kinetic energy. You can lose some of it. But it's that sticking together which causes the maximum loss of kinetic energy. It doesn't mean you lose all of it. It just means it's a situation where you would lose the most of it. So when things collide and stick, they lose the most kinetic energy they could lose. It could be all, usually is not. They'll have some. So that we're going to do a problem next that has a perfectly inelastic collision. We'll have Betty and Veronica. All right. One person's going to collide with another, grab on, hold. They're moving as a unit afterwards because they're sticking together. It's perfectly inelastic. There will be loss of kinetic energy in that problem. Okay, so I hope that kind of clears things up. Maybe I didn't. Maybe I just made things really confusing for you. But here's some real quick wrap up. You've got 3 different kinds of collisions. Some say 4, but remember the first 2 are the same thing. Elastic and perfectly elastic, the same thing. Okay, those typically don't happen. We will say, okay, something like billiard balls bouncing off, we'll call that elastic. Technically, it's not because there is a little bit of loss of energy, and that's the key. Loss of kinetic energy. No loss of momentum in any collisions. If you have an inelastic collision, that's where you are going to lose some of your kinetic energy, not momentum. And if it's perfectly inelastic, the things will stick together. All right, so here's what you've got. You've actually got between 2 ideals. You've got perfectly elastic and perfectly inelastic. And remember, perfect elastic is the same thing as elastic. So elastic collisions and perfectly inelastic. These 2 are the 2 norms, the 2 extremes, and everything norm is going to be somewhere in between. All right? This doesn't happen in IRL. In what we say on an everyday basis, you're not going to have this situation. We're going to have somewhere below this. Here, losing all perfectly perfect inelastic collision, when you lose all your kinetic energy, doesn't usually happen. It has to be a perfect set of conditions for that to happen. So our collisions are somewhere in between here, somewhere in between. The vast majority will be inelastic to some point, meaning we lose that kinetic energy. And if they stick together, we call those perfectly inelastic. Okay, all right, let's dive into a problem with this idea of 2 things are going to stick together, perfectly inelastic collision, and let's see what happens.